Welcome to this lesson on trigonometric integrals and trigonometric substitutions. These are powerful techniques for solving integrals that involve trigonometric functions or certain types of radicals. We'll cover two main topics. First, how to handle integrals involving products and powers of trigonometric functions, and second, how to use trigonometric substitutions to solve integrals containing specific radical expressions. Let's start with integrals involving trigonometric functions. When we encounter integrals with powers of sine, cosine, tangent, or other trigonometric functions, we need to use specific strategies based on the powers of these functions. For products of sine and cosine, we have two main approaches. If one of the powers is odd, we save one factor for substitution. If both powers are even, we use half-angle formulas. Let's work through an example to see how these strategies apply. Consider the integral of sine to the fifth power times cosine squared of x dx. Since the power of sine is odd, we'll use our first strategy. We'll save one sine term and convert the remaining powers using the Pythagorean identity. First, we rewrite sine to the fifth as sine to the fourth times sine of x. Then we use the identity sine squared equals 1 minus cosine squared to rewrite sine to the fourth. Now we have the integral of the quantity 1 minus cosine squared times sine of x times cosine squared dx. We'll use the substitution u equals cosine of x, which means do equals negative sine of x dx. This gives us negative the integral of the quantity 1 minus u squared times u squared, do. Let's expand the first term. We get 1 minus 2 u squared plus u to the fourth. Multiplying by u squared, we get u squared minus 2u to the fourth plus u to the sixth. Now we can integrate term by term. The result is negative times the quantity u cubed over 3 minus 2u to the fifth over 5 plus u to the seventh over 7 plus a constant. Substituting back u equals cosine of x, we get our final answer. Negative cosine cubed of x over 3 plus 2 cosine to the fifth of x over 5 minus cosine to the seventh of x over 7 plus c. Now let's look at an example where both powers are even. Consider the integral of sine squared of x dx. Since the power of sine is even, we'll use our second strategy and apply the half-angle formula. The half-angle formula states that sine squared of x equals 1/2 times 1 minus cosine of 2x. Substituting this into our integral, we get the integral of 1/2 times 1 minus cosine of 2x dx. We can integrate this term by term. The result is x over 2 minus sine of 2x over 4 plus a constant. Let's move on to our second major topic, trigonometric substitutions. Trigonometric substitutions are powerful techniques for dealing with integrals containing certain types of radicals. We have three main types of substitutions. For square root of a squared minus x squared, we use x equals a times sine of theta. For square root of a squared plus x squared, we use x equals a times tangent of theta. And for square root of x squared minus a squared, we use x equals a times secant of theta. These substitutions work because they convert complicated radical expressions into simpler trigonometric expressions. Let's go through an example of our first type of trigonometric substitution. Consider the integral of dx over the square root of a squared minus x squared. We'll use the substitution x equals a times sine of theta. This means dx equals a cosine of theta d theta. The radical transforms as follows. The square root of a squared minus x squared becomes the square root of a squared minus a squared sine squared theta, which simplifies to a times the square root of 1 minus sine squared theta, which is a times cosine theta. Substituting everything into our integral, we get the integral of a cosine theta d theta over a cosine theta. The a's and cosine theta cancel out, leaving us with the integral of d theta, which is simply theta plus c. To express the answer in terms of x, we need to go back to our substitution. Since x equals a sine theta, theta equals arcsin of x over a. Therefore, our final result is arcsin of x over a plus c. Now, let's explore an example of our second type of substitution. Consider the integral of the square root of x squared plus a squared dx. We'll use the substitution x equals a tangent theta. This gives us dx equals a secant squared theta d theta. The radical transforms as follows. The square root of x squared plus a squared becomes the square root of a squared tangent squared theta plus a squared, which simplifies to a times the square root of tangent squared theta plus 1, which is a times secant theta. Substituting into our integral, we get the integral of a secant theta times a secant squared theta d theta, which is a square times the integral of secant cubed theta d theta. For the integral of secant cubed, we can use the formula 1/2 secant theta tangent theta plus 1/2 natural log of the absolute value of secant theta plus tangent theta plus c. To convert back to x, we use secant theta equals the square root of x squared plus a squared over a, and tangent theta equals x over a. After substituting and simplifying, our final answer is x times the square root of x squared plus a squared over 2 plus a squared over 2 times the natural log of the absolute value of x plus the square root of x squared plus a squared plus c. To summarize what we've learned today, for trigonometric integrals, we have specific strategies based on the powers. If one power is odd, save one factor for substitution. If both powers are even, use half-angle formulas. For trigonometric substitutions, we match the type of radical. For square root of a squared minus x squared, use x equals a sine theta. For square root of a squared plus x squared, use x equals a tangent theta. For square root of x squared minus a squared, use x equals a secant theta. Remember, the key to mastering these techniques is recognizing the pattern and practicing with many examples. Thank you for watching this lesson on trigonometric integrals and substitutions.